In previous classes, we learned about the structure of atom, how the fundamental particles are arranged in the atom. We discussed about Bohr-Sommerfeld atomic models, and these two give a new direction to the understanding of atomic structure. In 1930, Louis de Broglie proposed the particle and wave nature, that is, the dual nature of the electron. According to de Broglie hypothesis, an electron in motion exhibit wave-like properties. Already we know that electron is a particle. When it is in motion, it exhibits wave-like properties. That means the nature of electron is wave as well as particle. That is the dual nature. In atom also, the electron is in continuous motion. Therefore, electron exhibit wave-like properties inside the atom. And based on the dual nature of electron, the quantization of its angular momentum is explained. Already according to Bohr's second law, we studied about the quantization of angular momentum, that is mvr equal to nh by 2 pi, where n is an integer 1, 2, 3, etc. The angular momentum is quantized. It can be expressed as an integral multiple of a fundamental quantity, that is h by 2 pi. And this idea is given on the basis of de Broglie hypothesis. And Schrdinger, he developed a wave equation for electron in hydrogen atom. And this gives the complete picture of atomic structure. And according to this wave equation, Schrdinger proved that the electron can exhibit at different energy levels. That is, the solutions for Schrodinger wave equation gives the idea of sub-energy levels that an electron can exist. These are called atomic orbitals. And this equation, the Schrodinger equation, gives the limiting values of various quantum numbers proposed during this period. The quantum model of atomic structure, or we can say the modern concept of atomic structure, based on the following postulates. The first one is, atom consists of several stationary states or stationary orbits. These states are designated by the value n, small n. This already we discussed in case of Bohr atomic model. There also we discussed that electron moves around the nucleus in particular energy states. These are indicated by n equal to 1, 2, 3 or with letters k, l, m, n. The second postulate is each stationary state. This is divided into substates, and these substates are called sub-energy levels. And the number of substates depends on the value of n. And these substates are designated by small l values. And l attains the values 0, 1, 2, 3, etc. Suppose we consider the first stationary state, that is n equal to 1 or k shell, and this is having only one sub-energy level, only one substate. In case of second, n equal to 2, it is having two sub-energy levels. Corresponding to this, the values of L is L equal to 0, 1. Similarly, for n equal to 3, L equal to 0, 1, 2. This is having three sub-energy levels. For n equal to 4, the values of L are 0, 1, 2, 3. These sub-energy levels are designated by S, P, D, F, G, etc. Suppose we take this for n equal to 2, the values of L is 0, 1. That means related to n, L attain 0 to n minus 1, n discrete values. This n is called principal quantum number, and this L is called azimuthal quantum number. The principal quantum number gives the main energy level, and azimuthal quantum number defines the sub-energy levels that present in a main energy level. For n equal to 2, the values of L are L equal to 0 and L equal to 1. And L equal to 0 is designated as S, L equal to 1 is designated as P, and these sub-energy states are called orbitals. That means this is s orbital and this is p orbital. That means this is main energy level, n equal to 1, 2, 3, 4. This main energy level is having sub-energy levels related to n equal to 1. One sub-energy level exists, that is s orbital. For n equal to 2, the value of L is 0 and 1, that is s orbital and p orbital. For n equal to 3, yes, it is 0, 1, 2. 0 related to s orbital, 1 related to p orbital, and 2 related to d orbital. For n equal to 4, the sub-energy states are 4, L equal to 0, 1, 2, 3, related to s, p, d, f orbitals. It is clear that we can divide the main energy level into sub-energy levels. Again, when magnetic field is applied, that is under the influence of magnetic field, these substates are further split into groups of states. When you apply the magnetic field, again S level, it is having only one substate. When you apply the magnetic field, suppose if I take P state, that is P orbital, this is divided into three different states. This further splits into groups of states. This P splits into three different states. D splits into 5 different states. F splits into 7 different states. That means when you apply the magnetic field, under the influence of magnetic field, the motion of electron gets different orientations, and each orientation are related to each sub-energy level that present in an orbital. Consider p orbital. P orbital related to L equal to 1. When you apply the magnetic field, this splits into -1, 0, 1, and these are related to px, py, pz orientations of p orbital. That means when magnetic field is applied, L further divided into 2L plus 1 values, that is minus L2 plus L. This is the magnetic quantum number. Suppose if I take L equal to 3, when magnetic field is applied, how many sub-energy levels it can have? It is 2L plus 1, 2 into 3 plus 1, that is 7. And these 7 states are -3, -2, -1, 0, 1, 2, 3. Similarly, if L equal to 2, an application of magnetic field, it splits into 5 sub-energy levels, that is 2L plus 1, from -2 to +2, including 0. This table gives the overall idea related to the sub-energy levels that present in a main energy level. For main energy level n equal to 1, this is denoted by k, and this is related to principal quantum number. The substationary state present in the main state is S, that is the number of states is only 1, and the total number of orbitals that present in this is 1. For n equal to 2, this is principal quantum number. The azimuthal quantum number is S. L equal to 0, 1. N equal to 2 can be divided into 2 sub-energy states. L equal to 0 related to S. L equal to 1 related to P sub-energy state. Again, when you apply the magnetic field, the number of sub-energy states that present in the sub-stationary state is, in S, we are having 1. In P, 3 are there. Therefore, the total number of orbitals present in this state is 4. For n equal to 3, L equal to 0, 1, 2, that is S, P, D. This is substationary state. Again, in S, we are having only one substate. And in P, 3 are there. In D, 5 substates are there. Totally, the total number of orbitals present in this state is 9. For n equal to 4, n equal to 4 means the L values are 0, 1, 2, 3. They are S, P, D, F orbitals. Again, the substates present in this. In S it is 1, in P it is 3, in D it is 5, in F it is 7. Totally, the number of orbitals present in the given state is 16. Important thing, the sub-energy level depends on the value of L, and it is indicated by ML. Related to L, the values of ML are 2L plus 1. For L equal to 3, yes, it is 7. For L equal to 2, it is 5. Totally, in this, we are having 25 orbitals are present in this. And the last postulate related to this theory is the electrons are placed in the sublevels, they revolve around the nucleus, and in addition rotate on their own axis clockwise or anti-clockwise direction. That means the electrons which are present in these sub-energy levels, they move around the nucleus. At the same time, they rotate themselves either in anti-clockwise direction or in clockwise direction. Now from all this, we can conclude the position of electron in an atom is defined by some numbers. Those numbers are called quantum numbers. Quantum number is a mathematical representation which gives location and energy state of an electron in an atom. Now we discuss about the different quantum numbers with their possible values. First one is the principal quantum number. Already we know this quantum number. This is based on Bohr atomic model, and this is designated as N and can take only positive integer value such as 1, 2, 3, etc. If the principal quantum number is 1, the stationary state is K shell. If the principal quantum number is 2, the stationary state is L shell. If it is 3, it is M. If it is 4, it is N. This principal quantum number gives the size and energy of stationary orbit. As the value of N increases, the size and energy of the orbit is also increases. The orbit which is nearer to nucleus, it is having least energy. When you are moving away from the nucleus, the energy increases. In general, the energy of an orbit is inversely proportional to square of principal quantum number, that is E proportional to 1 by n square, and the number of sub-energy levels in a given shell equal to n square. The next one is the azimuthal quantum number. This was proposed by Sommerfeld, and this is the result of elliptical orbits. This is also known as angular momentum quantum number or subsidiary quantum number. The electrons in atoms are grouped not only in main energy level but also in sublevels. These sub-energy levels are due to orbital motion and they are given by L. Related to a principal quantum number n, the electron can have n discrete L values, that is n discrete orbital motions. Already we discussed in Sommerfeld model. Suppose if I take n equal to 4. Related to n equal to 4, the possible L values are L equal to 0, L equal to 1, L equal to 2, L equal to 3. That is 4 discrete energy levels are there. Related to a principal quantum number n, the number of values that L can have are 0 to n minus 1. And these sub-energy levels are named as S, P, D, F, G. That is, if L equal to 0, it is named as S. L equal to 1, it named as P. L equal to 2, it named as D. L equal to 3, it named as F. For L equal to 4, it named as G. Simply, the principal quantum number gives the main energy level and azimuthal quantum number gives the sub-energy level that present in a main energy level. Already you know S, P, D, F. These are the names of orbitals. Discuss what are orbitals later. The next quantum number is a magnetic quantum number. This is denoted by M or ML, and this is proposed by Landé, and this gives the different orientations of electron in an orbital. When an atom is placed in an external magnetic field, the electron present in substationary state or subshell It orients in different ways depending on their energies. And these different orientations represented by the magnetic quantum number. Say this is a sub-energy level. When you apply the magnetic field, this sub-energy level can get this orientation, and this orientation. When it is at this position, this is related to L equal to 1 and this is related to M equal to 0. When the magnetic field is applied, it can orient like this. Now this is represented using ML equal to -1 and this can also orient like this. This is represented using M equal to 1. That means related to L equal to 1, the values of magnetic quantum numbers are -1, 0, 1. Similarly, related to L equal to 3, the values of magnetic quantum number are -3, -2, -1, 0, 1, 2, 3. Totally 7 values. That means related to a sub-energy level L, the number of sub-energy level we have 2L plus 1. Now the question is, what does this gives? If I take principal quantum number that gives the main energy level, it is okay. Azimuthal quantum number, it gives sub-energy level that present in a main energy level, that we are calling it as an orbital. Again, when we come to this, what does this gives? This is nothing but the different orientations that orbital can have. Suppose we take S orbital. The shape of S orbital is spherical. How many orientations can it have? When you apply the magnetic field, yes, it can orient. Whatever may be the orientation, it can have only one discrete energy level. In case of p orbital, it is dumbbell shape. When you apply the magnetic field, it can orient like this along x-axis, along y-axis, along z-axis. Now this is px orbital, this is py orbital, this is pz orbital. The different orientations that p orbital can have, px, py, pz. These orientations are given by magnetic quantum number. Similarly, if I take d orbital, d means L equal to 2. Now, what are the different magnetic quantum numbers it can have? -2 to 2, 2L plus 1, that is 5 values. The different magnetic quantum numbers are -2, -1, 0, 1, 2. These are related to the different orientations in d orbital: dxy, dxz, dyz, dx square minus y square, and dz square. This is about the magnetic quantum numbers. The next one is spin quantum number. In 1925, Unhalen-Beck and Goudsmit, they suggested that a moving electron around the nucleus can also rotate itself, that is, can also rotate on its own axis, either in clockwise direction or in anti-clockwise direction. And such a spin would contribute to the angular momentum of the electron. And the electron can spin along clockwise direction or anti-clockwise direction. They are represented by arrow marks. This is clockwise and this is anti-clockwise direction respectively. And the spin is quantized. The spin energy of electron is also quantized in units of half integrals, can take only +1/2 or -1/2. A sublevel, that is an orbital, can accommodate 2 electrons provided their spins are opposite. That means in a orientation, suppose if I consider px orientation, in this px orientation we can have only 2 electrons. One is having clockwise spin, another is anti-clockwise spin. Why? Because already we know that the angular momentum of this energy level is quantized. And now we discuss in detail about the atomic orbitals. Already we know that the atomic orbitals are sub-energy levels that present in a main energy level. And according to our previous discussion, we can conclude related to a main energy level n, 0 to n-1 and discrete energy levels are present. And these are orbitals. If I take n equal to 3, the L values are 0, 1, 2, 0 related to s orbital, 1 related to p orbital, 2 related to d orbital, etc. Now what is an orbital? Orbital is nothing but a space where we can find the probability of existing electron. Can you see electron? No, we can't see electron. We can't see electron accurately, and also we cannot estimate whatever the position of electron at a particular time. That is, we cannot measure the uncertainty in position and momentum of electron at a time, which is given by Heisenberg uncertainty principle. We cannot locate the electron accurately, but we can give some probability to find electron in an orbit. Electron is not stationary, it is in motion. Now in this orbit, the location where we can find electron more probably, that is called an orbital. How we can define orbital? An atomic orbital is nothing but where the electron is likely to move, or the area where we can find electron more probably. Atomic orbital is plotted by drawing the boundaries of the region where the electron is likely to move around the nucleus. The first one is s orbital. This is spherical in shape, as you are seeing in the figure. In this diagram, these dots, they show the position of electron at a given instance. Since the electron is continuously revolving around the nucleus, they are represented by dots depending on probability of finding of electron at a particular time. If more dots are present, we can say the probability is more to find the electron in this region. And it should be noted that it is difficult to draw the boundary for this dotted region as it is diffused. This is the shape of 1s orbital, x-axis, y-axis and z-axis. It can have only one orientation, and s orbital of first energy level, that is k shell, it is called 1s. This 1 refer to principal quantum number and s refer to azimuthal quantum number. Similarly, 2s means the s orbital in second energy level. 3s means s orbital present in third energy level, etc. All s orbitals are spherical. However, 2s, 3s, 4s, these orbitals will be having nodal regions. These nodal regions corresponds to 0 probability for locating an electron in that region. Next, p orbital. P orbital related to L equal to 1. It is denoted by p orbital. And there are no p orbitals in first energy level. Why? Because n equal to 1, L equal to 0 can exist. For n equal to 2, we are having L equal to 0 and L equal to 1. Here we have p orbital. And the shape of p orbital is dumbbell shape. And this p orbital can have 3 different orientations. And these are designated by px, py, pz orbitals, as I was saying in the figure. This is px, this is py, and this is pz. And next one is d orbital. This is related to L equal to 2. And they starts from n equal to 3 sub-energy level. L equal to 2 means how many orientations it can have? Yes, it can have 2L plus 1. 5 orientations. They are -2, -1, 0, 1, 2. That means d orbital can have 5 different orientations. They are dxy, dxz, dyz, dx square minus y square and dz square. And these 3 first orbitals, that is dxy, dyz and dxz, they lie in xy, yz and xz planes. And the orbitals dx square minus y square, they lie along x and y axis, and dz square, it lies along z axis. And these are the different orientations related to d orbital. And now we go for f orbital. F orbital related to, yes, L equal to 3. L equal to 3 means what may be the values of magnetic quantum number, as it can have 2L plus 1 values, that is 7 values, -3, -2, -1, 0, 1, 2, 3. And related to these 7 values, that is 7 different orientations can exist for an f orbital. Now these are the different orientations for f orbital. We learned about stationary states, quantum numbers, and atomic orbitals. Now the question is, in which order the electrons will fill up the orbitals as we build the periodic table? And this answer requires a knowledge of relative energies of atomic orbitals. Depending upon the relative energy of atomic orbitals, the electrons will be filled up, and the atomic spectra provides the information regarding the energies of atomic orbitals. And the order of energies are given by 1s less than 2s less than 2p less than 3s less than 3p less than 4s less than 3d less than 4p less than 5s less than 4d less than 5p less than 6s less than 4f less than 5d less than 6p less than 7s. The electrons occupy orbitals with lower energy. Molar has given a simple procedure to represent the orbitals of increasing energies. Of course, the order is same as we discussed earlier, and according to this procedure, the orbitals of increasing energies as represented with a diagram. This is the diagram, and as per this diagram, first the electrons occupy 1s orbital, then 2s, then 2p and 3s, then 3p and 4s. After that 3d, 4p, 5s, and after that 4d, 5p, 6s, and after that 4f, 5d, 6p, 7s, and after this 5f, 6d, 7p, 8s. See in this diagram, in first step you write 1s, 2s, 3s, etc. in increasing order of s orbital. From this you start with 2p, there is no 1p, therefore it is 2p, 3p, 4p, 5p, 6p, 7p. After that 3d, 4d, 5d, 6d, and 4f, 5f. Now the energy levels, the increasing order of energy levels will be represented using these arrows. First it is 1s, then 2s, then 2p, 3s, just you join them diagonally, then 3p, 4s, then 3d, 4p, 5s, then 4d, 5p, 6s. Like this you join diagonally. And this is called Molar diagram, and this diagram gives the idea of increasing energies of orbitals. And this procedure is fully valid for lighter elements, but for heavier elements the order may change. For example, if I take lanthanum, the electronic configuration of lanthanum, the atomic number is 57, it is Xeon 6s2 4f1. But the correct electronic configuration of lanthanum is Xeon 5d1 6s2. That means in this case, the diagram is not valid. Therefore, we can conclude that this diagram should be used only as a guideline, keeping in mind the possible changes that can occur in heavy elements. Now, while writing the electronic configuration of atoms, we have to follow some rules. What is electronic configuration? Yes, the electronic configuration is a representation of occupation of electrons in the orbitals. No doubt, the electrons occupy the orbitals in the order mentioned earlier. Again, the filling up of these electrons into these orbitals are governed by Aufbau principle, this is called building up principle, Hund's rule, and Pauli's exclusion principle. First we discuss about Aufbau principle, this is called building up principle. According to this principle, the electron occupies the orbital having the lowest energy. Suppose we consider hydrogen atom. It has only one electron. No doubt, this electron enters into a 1s orbital. This is the lowest energy. And in terms of the quantum numbers, the incoming electrons go to an orbital whose n plus L is minimum. This is very important. N is the principal quantum number, L is the azimuthal quantum number. If n plus L is minimum means the energy of that electron is minimum, the electron enters into that orbital. If two orbitals have same n plus L value, then the orbital having lower n value will be occupied first. For example, if I take scandium. The atomic number is 21. These 21 electrons can be accommodated like this: 1s, 2s, 2p, 3s, 3p, and 4s orbitals. The last electron can enter into either 3d or 4p orbital. Suppose if I take this, 1s contains maximum of 2 electrons. This is 2, this is 6, this is 2, and this is 6 and 2. How much it is? 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20. Up to this, 20 electrons are completed. Now, the last electron, 21st electron, where it can be accommodated. Either it is in 3D or 4p. Suppose we consider 3D orbital. 3D, what is the n value? Yes, it is 3. What is L value? 2. Therefore, n plus L is 5. Similarly, 4p, n is 4, L is 1, 4 plus 1, 5. Both are having same n plus L value. Then where electron can accommodate? Yes, at 3D level. Why? In this case, the n value is less. Therefore, the electronic configuration for scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. This also can be written as the electronic configuration of argon 4s2, 3d1. Now in this notation, this subscript that represents the number of electrons present in the corresponding orbitals. This is the first rule what we have to follow. The second rule is Hund's rule. This states that the electron pairing takes place only after all available degenerate orbitals are occupied by one electron each. In general, we are taking electron pairs in orbitals. Suppose if I take 1s, how many electrons can it have? 2 electrons. One is with spin plus of, another is with spin minus of. Similarly, in p orbital, px, py, pz orientations are there. In px orbital, 2, in py 2, in pz 2, totally p orbital is having 6 electrons. But this pairing, suppose you are having 6 electrons, you can fill 6 electrons in p orbital with px2, py2, pz2, it's okay. When you ask it to fill with 3 electrons p orbital, then how to fill? In this case, we have to follow Hund's rule. According to this, electron pairing takes place only after all available degenerate orbitals occupied by one electron each. Suppose we have to fill px, py, pz orbitals. We are having 3 electrons. Then these 3 electrons can be accommodated like this: 1 in px, 1 in py, 1 in pz. If 4 electrons are there, yes, then first you fill px, py, pz each with 1 electron, and 4th electron that will be paired to px electron. For 5 electrons, yes, first you fill these 3 with 1 each, then this is 4th and this is 5th. Like this we have to fill. For example, we take carbon. Carbon atomic number is Z equal to 6, that is, it has 6 electrons. Now how to arrange these 6 electrons? In first energy level, that is K shell, 2 electrons. That is, first electron goes into 1s orbital, the second will paired up with this 1s orbital, 2 electrons will accommodate in 1s orbital. Next 2 electrons will accommodate 2s orbital related to L shell. Now the 5th electron, 6th electron, 2 electrons are left. Now how to arrange these 2 electrons? In 2px? No, not in 2px. Why? Because px, py and pz all are degenerate levels. First you send 1 electron to each degenerate level, then you start pairing. Here 2 electrons are available. One will accommodate in 2px, another at 2py. Therefore, the 5th electron goes into 2px and the 6th electron goes into 2py or 2pz, but not in 2px. Therefore, the electronic configuration of carbon is 1s2, 2s2, 2px1, 2py1. In this case, this up arrow indicates the spin of electron plus 1 by 2, down arrow indicates the spin of electron minus 1 by 2. Similarly, we take nitrogen. Atomic number is 7. It is having 7 electrons. First 2 electrons, these are sent to 1s, next 2 to 2s, 3 are remaining. The 3 will send to 2px, 2py, 2pz, each 1. Suppose if I take oxygen, Z equal to 8. How many electrons are there? 8 electrons. 8 electrons means in first energy level, the maximum number of electrons is 2. In second energy level, the maximum number of electrons is, yes, it is given by 2n square. The maximum number of electrons in second level is 8. Now here 2 electrons, they are sent into 1s orbital. The remaining are 6 electrons. In this 6, 2 electrons are sent to 2s orbital. The remaining are 4. First you fill, these 4 are sent to 2p. But first you send first 3 electrons into px, py and pz. After filling this, the pairing will be started with px. The 4th electron will go to 2px. Therefore, the electronic configuration of oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1. Now this is the electronic configuration of oxygen. Now the next principle we have to follow, Pauli's exclusion principle. According to this, no two electron will have all the 4 quantum numbers same. That means no two electrons can exist at same quantum state, or no two electrons can have same quantum energy. And according to this, no two electrons will have identical n, l, m, s values. And this restricts the number of electrons in a single orbit to 2. Suppose we consider 2 electrons. Let us say these 2 electrons are having same principal quantum number n. For example, n equal to 2 for each. What does it mean? 2 electrons are related to second stationary state, that is second energy level, that is L shell. Even though the value of n is same, the azimuthal quantum number L may not same. For one electron, L value may different for another electron. Already we know that if L equal to 0, it is s orbital. If L equal to 1, it is p orbital. For n equal to 2, the maximum number of L values are 2 only. That is L equal to 0 and L equal to 1. In this case, L equal to 0 represents s orbital, L equal to 1 represents p orbital. Even though the 2 electrons may have same principal quantum number, they may exist in same main energy level. The sub-energy level may different. That means one electron may belong to s orbital, one may belong to p. Again we consider L is also same for these two. Let us consider L equal to 1 for both the electrons. Then the magnetic quantum number is not same. Already we know that related to L equal to 1, the possible values of magnetic quantum number are -1, 0, 1, that is 2L plus 1 values. This represents px, py and pz orientation of orbitals. Even though 2 electrons may present in p orbital, one may in px, one may in py, that is the magnetic quantum number may different. Again, if magnetic quantum number is also same, suppose both present in py orbital, then the spin quantum number may not same for 2 electrons. Definitely one electron is having plus 1 by 2, the other is having minus 1 by 2. That is, one is spin up, another is spin down. One has clockwise spin, another has anti-clockwise spin. Like this, no two electrons in an atom can have 4 quantum numbers n, l, m, s are same. No two electrons will have identical n, l, m, s values. This is Pauli's exclusion principle, and this restricts the number of electrons in a single orbital is 2. Now using these three rules, Aufbau principle, Hund's rule and Pauli's exclusion principle, we can write the electronic configuration of elements. This table gives the electronic configuration of elements. Some elements, just you see here, first I am taking lithium. The atomic number of lithium is 3, Z equal to 3. How many electrons it has? 3. Now first shell has 2 electrons. It is 1s2 and the second 1 electron is remaining. This electron sent to second shell. Therefore, the electronic configuration of lithium is 1s2, 2s1. This can be written as helium 2s1 represents electronic configuration of helium which is 1s2. Why we are writing helium and 2s2? This helium, it is inert gas. It is having completely filled first orbital. The valence of helium is 0. While writing the electronic configuration of valence electrons, first you write the completely filled element. After that, you write the remaining electrons. Similarly, we take argon. Argon, the atomic number is 18. Already we know that the first orbit, the maximum number of electrons in first orbit are 2. In second orbit, 8. In third orbit, 8. It follows a rule 2n square. Suppose if I take 18 electrons, how many orbitals can be completely filled with 18? Yes, first orbit can be filled, second can be filled. First orbit, first 2 shells can be completely filled. First shell 2 electrons, second shell 8 electrons, 10 electrons. Now what are the remaining electrons? 8 electrons. First 2 shells are completely filled. That element related to neon. Therefore this can be written as neon 3s2 3p6. Similarly for potassium, if first 2 shells are completely filled, the atomic number of potassium is 19 and 9 electrons are remained. The electronic configuration of neon is Ne 3s2 3p6. What is the next? Is it 3d or 4s? It may be 3d1 or 4s1. Now it is 3d1 or 4s1 that we have to check with Aufbau principle. That is, for which n plus L value is minimum, that state electron can occupy. For 3d orbital, the value of n plus L is 3 plus 2, it is 5. For 4s, 4 plus 0, it is 4. For which n plus L is minimum? Yes, for 4s it is minimum. Therefore, the electronic configuration of potassium is neon 3s2 3p6 4s1, or it also can be written as argon 4s1. Similarly, the electronic configuration of vanadium with atomic number 23, this can be written as argon. Argon means it is 18. The remaining electrons are 5, 4s2 3d3. For chromium, atomic number 24, 18 plus 6, this can be written as argon into 4s2 3d4. For nickel, with atomic number 28, argon into 4s2 3d8. For copper, atomic number 29, argon into 4s1 3d10. But experimentally it was found that the electronic configuration of copper is argon 4s1 3d10. Why? The reason is 3d10, it is completely filled configuration. It is more stable compared to this. Therefore, the electronic configuration of copper, that is cuprum, it is argon 4s1 3d10. We can observe that the electronic configuration of heavier elements do not strictly follow the above rules. Whatever the stable configuration that they attain. Similarly, if we consider chromium, we written the electronic configuration of chromium is argon 4s2 3d4. But experimentally it is argon 4s1 3d5. This is also due to 1. The degenerate orbitals are off filled, are completely filled. Then it gets the stability. 3d5 is off filled, all d orbitals are off filled. Therefore, this is the most stable configuration compared to this. This is how to write the electronic configuration. According to Pauli's exclusion principle, we can give the maximum number of electrons that a shell can have. For n equal to 1, the value of L is L equal to 0, the maximum number of electrons 2. For n equal to 2, the values of L are 0 and 1. 0 means it is s orbital, 1 means it is p orbital. S orbital can have 2 electrons maximum, p orbital. Again, this can be divided into px, py, pz. That means related to these L values, the values of m are, for this it is 0, for this it is minus 1, 0, 1. It is px, py, pz orbitals, and each orbital can have 2 electrons. Therefore, the maximum number of electrons 2 plus 6, it is 8. For n equal to 3, what are the values of L? Yes, L equal to 0, 1, 2. 0 means s orbital, 1 means p orbital, 2 means d orbital. Again for L equal to 0, the possible values of magnetic quantum number. M equal to 0. For L equal to 1, minus 1, 0, 1, px, py, pz. For L equal to 2, that is d orbital, the possible magnetic quantum number values are minus 2, minus 1, 0, 1, 2. That is dxy, dxz, dyz, dx square minus y square and dz square. Now the maximum number of electrons, for this it is 2, for this it is 6, for this it is 10. The maximum number of electrons in third shell is 18. Just you observe these values. The maximum number of electrons in a main energy level with principal quantum number n in a shell are 2n square.